So here we will talk about waves on a string. I've taken the example 15-1 from Tipler and Mosca. We're not going to work out the example yet. We're just going to talk about what happens if you strike a string. So in this particular picture, the lady in this picture is striking the string at this point over here, and that causes a traveling wave. The wave is going to travel to the left. So because the wave is traveling to the left, we need to know how fast is the wave moving. In this picture, you see that the rope or the string that is on which the wave is going to travel is hung over here with a mass at the end. And so essentially what we are saying is that the string, if I draw it over here, there is a tension on the string. So the string is being pulled in this direction because of the presence of this mass. And how much is that tension? Well, the tension is equal to the mass times acceleration due to gravity for the mass that is hanging over here. So this tension Ft, let's call it Ft, that Ft is equal to m times g. In the picture, we see that the mass m is equal to 10 kilograms. Acceleration due to gravity, we know that is 9.8 meter per second squared, which means Ft is equal to 98 Newton. So that's the tension in the string. It turns out that if we know the tension in the string, and if we also know the mass per unit length of the string, so mass per unit length, we will represent it by this fancy character mu, this Greek letter mu. And mu is nothing but a fancy way of writing the mass of the string. So that's different from the mass we are using. Mass of the string divided by the length of the string, right? So if we know the mass of the string and the length of the string, we can figure out the mass per unit length. In this particular problem, the mass of the string is given to be ms equals 1 kilogram, and the length of the string is given to be 25 meter. So knowing these two quantities, then we can find that the mass per unit length is 1 over 25 kilogram per meter. All right, so we can use this information to find the phase velocity of the wave that's moving along this string. And in order to do that, we'll need this formula, V equals square root of the force of tension divided by the mass per unit length. So this is again a formula that we're not going to derive over here. The derivation is given in section 15-2 of the book, and I encourage you to look it up. But we're going to just use this formula. Velocity of a wave on a string looks like V equals square root Ft, the force of tension on the string, divided by mass per unit length of the string. Okay, so in order to use this, we're going to have to plug in what we know about Ft and mu. So Ft, we know that Ft is m times g, so we will put it in mg divided by mu. Mu is ms divided by ls. So that becomes V equals square root mg times ls over ms. Okay, now rest of it is just putting in our numbers. At this point, we can just plug in our values to figure out the velocity. So this velocity is square root of m is 10 kg, and I encourage you to keep the units at every step. 10 kg times 9.8 meter per second squared multiplied by ls, which is 25 meter, divided by ms, the mass of the string is just 1 kilogram. So you see that the kgs will cancel, and then I have meter times meter per second squared, so that's meter squared per second squared. But we have a square root, so the stuff that comes out is just a meter per second. And then square root of 25 times 98. So that's my answer, and it's divided by 1. Great, so this looks like this is going to be 5 times 7 times square root of 2 meter per second. And I did that because, remember, 7 times 7 is 49. 5 times 5 is 25. So when I take the square root, I get a square root of 25, which gives me the 5. 98 is a 49 times 2. So square root of 49 is a 7. And then I have a square root of 2. So that becomes 35 square root of 2 meter per second. And I could put in the value 35 times 1.414, which is the square root of 2 meter per second. I get 49.5 meter per second, roughly. So that's the speed with which the wave is traveling on the string. Let's talk about a few more interesting quantities associated with waves on a string. Well, first we learned about wave velocity. So that is v equals square root ft over mu, where ft is the string tension and mu is the mass per unit length. So mu is equal to mass of the string divided by the length of the string, right? And then we learned about angular frequency of waves. Angular frequency of the waves is just represented by omega. Amplitude of a wave, which is a. Now you can kind of imagine that if there is a wave, there's something that is oscillating, so that oscillating object probably has some energy. So how do we measure the energy for a wave on a string? It turns out that this energy will depend on how much length of the string or length of the wave that you're considering. So if you consider delta x length of the wave, then it turns out that the average energy in that amount of length delta x is given by delta E average is equal to 1/2 mass per unit length of the string multiplied by the wave frequency squared, angular frequency squared, multiplied by the amplitude squared times delta x. So the average energy is proportional to the mass per unit length. So if you increase the mass per unit length, if you consider a string that is sort of denser, right? I mean, it has more mass in every unit length, then you'll have more energy. That's kind of understandable. And then if you have a higher frequency wave, then you'll have a higher energy. If the amplitude of the wave is higher, which means that the oscillations are larger. So this part is the amplitude of the wave, right? So if I increase the amplitude of the wave and make it go back and forth over a larger distance, then the energy will increase. And then if you consider a longer length of the string, it's understood that the energy will be more. So that's the average energy for a string. And from the average energy, we can also talk about an average power. So we'll talk about P average power. Remember from our UP1 class, power is work per unit time. And work and energy is sort of the same thing. So power in this case is delta E average divided by delta T, where delta T is the time unit over which we're measuring this delta E average. So if I plug that delta E average from this first formula in here, I get 1/2 mu omega squared a squared delta x divided by delta T. Okay, but delta x over delta t, that's the wave velocity, right? So if that's the wave velocity, then we can write this equal to 1/2 mu omega squared a squared times v. So that's the average power for waves on a string.